But first, I want to introduce our first plenary speaker, Jane Watson. I was delighted when Jane accepted my invitation to speak to us today. Jane came a very, very, very long way to speak to us from the University of Tasmania, which of course is in Australia. But Jane is not a native Australian. Some of you know Jane and know that she's a native of which state? Not California. Good guess, though, since California is the most populous state. Jane is a native, very statistical guess. Jane is a native of the great state of Kansas. She got her PhD in mathematics education at Kansas State University. She actually grew up in Manhattan, Kansas. We do have some K-State people in the room, it seems. And Jane, while she was working on her PhD, she received a Fulbright Award, and she went to Australia for her Fulbright, and she has spent her entire career in Australia since then. She's very well known in mathematics education, especially in statistics education. She's been very involved in USCOTS and ASA and SURGE and lots of international efforts related to statistics education. She's published literally hundreds of articles, received millions of dollars in funding, and received several awards for her research work. One thing I think I'm safe in saying is that Jane believes strongly in connecting educational research to classroom practice. And I invited her to be the first keynote speaker at this conference so that she could provide all of us with a perspective as to what K-12 students can do and perhaps should be doing with regard to evaluating evidence in their school classrooms. So thanks again for coming, Jane. We look forward to what you have to say. I'll give you the floor.
Thank you. Okay, so the idea is that I use this. Is this okay? Can you hear me all right? Okay. Because if I had one of those, I'd be wandering all over the place. Before I start, I want to tell you about an email that I received this morning. It is from my and your dear friend, Chris Franklin. And she was sort of wishing me good luck because she can't be here. But do you realize that almost the same time, just probably a few hours ago, because of 6 hours difference between here and South Africa, she was giving a keynote talk to a conference, I think it was, I don't know if it was PME or one of the conferences in South Africa. So we've been comparing notes back and forth about, our nervousness and our giving talks. But I thought you'd all like to know that Chris is thinking about you, and I'll be thinking about me as well. Okay. I'm going to start with some of the background that I'm sure you all know, but it's the sort of thing that I talk about with teachers in Australia, and they don't know. So first of all, I've got a little bit of history for you. You all know from the 80s, when I was teaching even in a math department, not in an education faculty, about the quantitative literacy project. And I love this because I don't know if you've read Lynn Arthurstein's Confession. You know what the Confession is? What should that series be called? Statistical literacy. But they named it quantitative literacy instead because they figured nobody would buy it if they called it statistical literacy. So I just find this really interesting how we adapt our names for what it is that we think people will buy. And in the middle 80s, they didn't think that teachers would buy something on statisticals. Too big a word. And then this is the sort of 80s and 90s transition. And I will say that the statistics text on the left is Chris Franklin's favorite, and we do a lot of comparing about what the best things are. But the book that I actually first taught statistics from was, I was a tutor in lots of other statistics courses before I joined education. But we actually had a program one year where we had a specialty that you could do mathematics as pre-service primary teachers. And that was the book that I used. It was 1989, and that was the year that that book came out. And the practice of statistics has been now what I use because, another coincidence, when Danny Bensfee started his idea about having a handbook for statistics education research, which some of you may know about, and I know some of you have contributed to, they, whoever they are, named the first chapter about, in section whatever, the practice of statistics. And Sandy and I and a couple of others were authors of this chapter, and we didn't have any choice about the title. That was the title. And I thought, great, I love it, because I remember Maureen McCabe. And why not use that for work with children? And there are a lot of controversial names that we use for when we're doing statistics, and you'll see a few of them in a minute. But I'm thankful to Maureen McCabe and to Danny and his crew. And then I'm sure you're aware that it wasn't really until 1989 when the NCTM actually put out the first standards that statistics, data, and probability, chance was in the curriculum. And then in 2000, the later principles and standards came out. Now, other countries followed this, particularly Australia and New Zealand were very close behind in looking at this. So we were working in the same sort of way, following the NCTM. And you'll see at the end, if I get to the end, I'm still a great fan and worker with the NCTM. And then we're all aware, I'm sure, of Wild and Fancook and their work and their PPDAC. Now, I'm afraid I don't use PPDAC with children. We talk about words instead. And as you know, they were working with their actual applied statistician colleagues. And so this is actually what statisticians do. And educators have obviously translated that very easily into what we do at school in a simpler way. And you can see that, I can't remember exactly who has created this cycle, but it's often used in papers in school journals in terms of what we do. And of course then, in 2007, we have Chris's GAISE report for schools. And I noticed that people were talking about GAISE yesterday, and I take it you were talking about the college one yesterday. But this is the school one, and it's got the same sort of issues. And what I loved about it, because variation is my thing, that the way it's stated in that particular report, every heading says anticipating variability, acknowledging variability, accounting for variability, allowing for variability, so that it keeps coming through all the time. Now, this is how we translated this, and I'm going to be talking about 3 projects across this time. And the first project was in the city of Brisbane in Australia with my colleague, Professor Lynn English. And we had a 3-year project. We were working with the same group of students, 4 classes, the whole school, from grade 4 to grade 6. And we started off in the beginning with this. We didn't want to use that complicated one because what we were dealing with. And so we had this as a poster on the wall for 3 years for the students. Every time we moved to a new class, we did it. And then we did it in different ways. We didn't always do the complete activity. Every activity wasn't completely like that, but that was what we had as our background. And the other thing that I talk about a lot in Australia, the Australian Association of Mathematics Teachers is equivalent to the NCTM, and I must admit that I put some pressure on them, and a couple of years ago, Chris came out and did a keynote for them, and my golly, was she popular. She was mobbed. So, you know, she's everywhere in the world. Anyway, they put up a website called Top Drawer Teachers. And I would suggest that you might go and look for it, except that be careful when you put in top drawer, because you're likely to get a lot of lingerie ads. But if you put in teachers, then it might come through. And my colleagues and I did a drawer on statistics. And the rule was that you had to have no more than 5 big ideas that underpinned what you were doing. And so these are my 5 big ideas, and I know that other people have 8 big ideas. I think Danny and Joan had 8 in their book, and various people have 8, but we only allowed 5. And so I've been talking about this pentagon in Australian schools for a few years now, and obviously down the left corner, variation is the foundation of everything. Without it, we all know we wouldn't have statistics. But from it, we want to harness variation with expectation, and that comes out in 2 ways when we sort of get to the point of talking about what's the typical value, the mean, whatever, or the probability. What's the probability going to be grows, as we all know, the expected value, that when we get higher up. Students don't know that term, but we talk about probabilities. But to look at those two, we need distribution. And distribution turns out to be one of the really fundamental things. As Chris Wilde and others will tell you, that's how we look at variation and find the expectation if we're not just using formulas, is the picture. And then randomness, of course, is what we need in various ways in terms of talking about the probability that we do with expectation, and if we want to do random sampling, so we have the idea of randomness, which of course is one of the more difficult ideas for primary school. And then informal inference, and that term has been used a lot lately. Katie Maka and Andy Rubin, I think, have the foundation paper in that. And it's what evidence we have. It's not a p-value, which I know I don't have to argue much about anymore, but what is it that we can use as our evidence? So I may be coming back to this. But in relation to this, the three really important things are a context. And I don't know if you know about Rao's paper from 1975, but I've been using it forever. And as Ido was saying yesterday in his workshop, context is what makes sense. And variability more, and everybody talks about variation. But also for students is the importance of decisions about populations and the uncertainty that's involved when we do an activity. And I'm sure we're all aware in school math, sorry, by the way, sometimes I say maths, I'll try not to. The answer's always there. And one of the problems that I have in getting teachers to do chance and data is that they don't know what the answer's going to be before they start. And they have to know if the answer's going to be 27, but of course the answer may not be 27 when we do it with data. Okay, so what I'm going to do is I'm going to talk about some of the research projects that we've done, and I'm going to talk about the activities. I'm not going to talk about the p-values or anything that we did with the research. I just want to expose you to what children can do, some examples of what they do in the classroom. So I'm going to start with grade 3 and a project that we are just completing now, which is a STEM-based project. But what you'll see, you'll see that in a moment. Then I'm going to move on to an investigative cycle which uses the GAISE sort of thing that we did in an earlier project, the one with the steps in grade 5. And then what I want to do is introduce a rather interesting project that we had with some teachers in grade 10 in our school. The students have had a pretty abysmal chance and data curriculum up till then, but the teachers wanted to do something different with their grade 10, and they called the class advanced, although often when you go into a class you're not quite sure how advanced they are. But so this is a unit that we did with them. So that'll give you a range of the sort of things that I think can be done across the school years. Okay, the first one was making licorice sticks in grade 3. And the packet on your left is a brand of licorice that we have in Australia, which is strips. You can see it's not all sorts. I don't know if you have all sorts, but anyway, this is a strip. And it's about 8 centimeters long and about a centimeter in diameter. And I don't know if your parents or grandparents, if you know about Play-Doh and the Play-Doh extruder. When I talked about this in Portland, a lot of people said, oh yes, my children have those or whatever. And you have Play-Doh, and then the factory, or an extruder, will create by machine whatever the little form is. You can see the forms in the middle there. And there was a round one about 1 centimeter. So this is what we're going to do. We're going to make them by hand, 8 centimeters long and 1 centimeter in diameter, and we're going to weigh them and record the mass. Now, in grade 3, that's a lot. We're really reinforcing the measurement, the mass. There's all the mass in this, and the weighing. Many of them were not good at the weighing, but they were learning. Then do the same thing with the extruder and measure them, make sure that there's centimeter weight, and record the mass. So doing this twice. So here we have making them by hand, and here's our class. And you can see that they're very conscientious. Can you see Harry there? Is this the one? Harry, do you see what Harry's doing as well? This is grade 3, and he's obviously a fast worker. And so, and when we were going around taking photos, he wanted us to take a photo of that. So that group was having a lot of fun. So it's not, serious, but. And so then that shows them they're measuring the length and weighing the licorice sticks that they have created. So they did this on one day and recorded, and you'll see the results of the recording at the end, but I can't show you in 2 bits because I only took a photo at the end. So then the next day, they're doing it with the factory. And you can see the girl on the left is putting the Play-Doh in, and the boy on the right is squeezing it out. And then they have to cut it and measure it and then weigh it again. Okay, so this is a big exercise with lots of help in grade 3. So this is an example of one of the classes. And you will see on the right, the yellow are by the way, they had to write the weight mass on yellow stickies. And so those are the yellow stickies. They're all labeled, and not very neatly, of the masses of the ones they made by hand. Okay, so there was a big discussion about that. And what you will see are some purple ones. And because we're thinking about predictions as well. So after we had done it, we're thinking about expectation. If you made another one, what do you think? Or if Johnny came in, who hadn't been here, and he made one, what do you think his would be? Okay? So we've got these kids, some of these students who are, looking at the middle, and they were thinking, yes, that's the sort of thing. But you'll notice the one at the end on 30. That's someone who said, I really like licorice. So, the idea of looking at in grade 3, looking at the distribution is not maybe the most important thing, but that's okay. And then the one on the left is when we did it with the factory. And so then we were talking, obviously, about the difference, about the range. We were talking all about the values and why this might be the case. And this is then the second class, which was back-to-back with the first class. So the same thing happened. The purple ones in this class were the ones they did by hand, and then there were the yellow ones were the predictions that they might, if somebody came in. But then what happened? In the first class, what we did was each student made 3, as you saw, but they only were allowed to choose 1 to put up on the board because we had so many students. But in the second class, they got so excited, they wanted to put up more. And they actually had this kind of intuition about how much better somehow using the factory was. And so they wanted to do more. And the poor teacher is working, trying to get this up to the ceiling, and the kids are cheering, So, this is bringing all this life into this sort of thing. And by the way, just one sentence, it was a STEM project. So we were talking about the difference in variation when you have a manufactured product and when you have a handmade project. And we have a lot of crafts in our area. So we were talking about the difference between when mother makes me a sweater and when I buy it in the department store. And my colleague made a batch of chocolate chip cookies, and she made them all different sizes. Then we bought a packet from the supermarket, and we talked about the difference between the variation in the cookies, and we asked them, which would you rather have? And almost all of them said, I want the homemade ones. But they're likely to be bigger. So this is the sort of thing that we were doing in that project. So what we then asked the students was, they had workbooks, what is the difference between the two plots? And here are some of the things that they said. Now, these are grade 3s, and we have corrected the spelling, I will tell you. Once we made the hands were very different, were a little bit different. All right, that's pretty good. And then some of them talked about the range. Right, the machine is more accurate. That's a pretty big word for grade 3, although it probably wasn't spelled correctly. There are more different weights in the handmade. And then nobody in the machine-made had a 5-gram one, but one of the handmade people did. So they, again, they'll look at individual values rather than the whole shape. But then, this is so typical of younger children. I've seen this a lot in projects. The handmade one's like a city with homes spread out, and the factory one is the same, except the factory has tall buildings, but not many tall buildings. I mean, why not? That's their language. 14's more common. Handmade's like a city, but the other's like a tower, and have a larger typical number. So 4 months later, after this, because we do research, we're measuring statistical literacy at the end of each year, and we're going to write this up. This hasn't quite been done. So 4 years later, on the survey, we ask them, if you can just see the tiny print up there, it says sketch 2 graphs to show the data we collected. And then underneath that, they were supposed to write a sentence which explained their graph. Now, I'm pretty impressed that after 4 months, not all of them could do it, I will admit, but you can see that they haven't, you're going to say, they haven't labeled the graph. But I'm not upset about that. It's more squished together, and the handmade is spread out. Perfect. I'm really happy with the grade 3. But this one almost makes me cry, and I have to be very careful about this one. This is a little boy with, I think, what we call severe dyslexia. And you will notice you would be very critical of what you're seeing there. The spelling is terrible. Nearly all together is the methine, and then the non-methine is all apart. And there's some numbers up the top. And this little boy could not write that sentence, but he explained exactly that sentence to one of our helpers. We have one fellow who's on our team named Ben, who's actually a gymnastics coach, and he's very popular. And he would go around and say, well, what do you want to say? Because he just couldn't write the sentence, but he could say it. And that just makes my heart, I think I would have been a good grade 3 teacher, maybe. So this was in grade 3, and they had no experience with TinkerPlots at all. But in grade 4, we're going to introduce them into TinkerPlots. And how do you do this? Well, you use data that is meaningful to them. And so now what I'm going to do is to show you what we got them to do with their data. And with Bob's help, I'm going to... Now, I have asked a couple of people if they know TinkerPlots, or, and some, when we were sitting around tables, say, yes, I do, and others say, no, I don't. Well, I think TinkerPlots is the dream world program for school level, and probably even some of the introductory work you do. Okay, so this is, we talked to them about how we set this up, and that they had that little blurb down the bottom, that we had 2 methods that we used, and then we had the mass that we collected. And so it did not take very much at all to teach them how to drag down a plot. But what's interesting maybe for you, we all know what we would do, and in fact, I'm going to do a little bit of what we would do. Why are there 2 colors? We talked about, well, why are there 2 colors? Because some were factory and some were handmade. Then if we want to look at the mass and see if there's a difference, we drag the mass to the horizontal axis. And lo and behold, it changes color, and we've got 2 bins. And the students got bins. What's that? They're floating. And you people, and we would say, But of course, TinkerPlots is such that you can grab an icon and you can move it, and you then have more bins. And one of the things that we do is all of us do this. because that's what we expect. And I'll tell you what we do next, we stack it. But students don't necessarily have to look at it on the axis if they're not used to axis. They can look at it in a couple of bins and say, look, most of them are between 15 and 12 and 15. And that's, right. And they can stack the data, right? And they can actually, and they will, they don't necessarily do what you and I would do. They can colour it. Look, most of the factory ones are in there. And of course then we let them show all the things that they can do, and then we do, get them to looking at on the axis. And then, as you may know, that you can either drag it or you can then pull it up and you've got the factory. Now that's the data from one of the classes, and they can then talk about how that compared with what they did. So that we then use TinkerPlots all the way through to help them develop those skills as well as lots of handmade work. So I can get rid of that. I don't need to say that. Go back to here. All right. And now I'm probably going to have to talk faster. Is that right, Alan? I'm 20 minutes, 24 minutes. Okay, now I'm moving on to grade 5. This is a different project. This was the project in Brisbane. That previous one is one that we did in Hobart. And this one we got, was very complicated. What these students had done in grade 4 was they had done an activity on problem posing in the playground. What do we need to do to ask questions? What do we need to better the program and all that sort of stuff. Then we had looked at an activity on variation. And what we'd done is we'd measured one student in the class. Everybody in the class measured Antonio's arm span, and we had that. And then we measured everybody else in the class just once. And so we were looking at the plots and the difference between that, and we did it by hand and we did it in TinkerPlots. So they were used to that. And then they had done an activity with 2 coins modeling uncertainty, and that one is much more probability modeling, and that one's written up in JRME. So the context, and I'm not going to read that, but you can just imagine what it says. In the Australian curriculum, we have cross-curriculum priorities, and luckily, sustainability is one of them. And so this was our aim in starting this activity. So the question that we were asking is, are we environmentally friendly? And how do we do that? Well, we have to have survey questions. And at grade 5 level, what we did was, because at that point the Australian Bureau of Statistics had a census at school site, and unfortunately due to financial cuts it doesn't exist anymore. But thousands of kids had responded to this, and so we had their questions. So what we were getting the students to do, and this is really complicated for grade 5, they had to plan the data collection that they were going to do in their class, collect data, analyze the data, draw a conclusion for their class, and then, where I'm saying, that's not enough, we have a population. I created a population of, I think it was 1,300 Year 5 students from around Australia and their answers to these questions. So we started talking about random sampling. And we said, well, we can take random samples because of our wonderful, beautiful TinkerPlots. So we can put the population into TinkerPlots, we can do random samples, we can compare them with our class, and then we can think about making a decision for Australia. Well, we'll see where we go. So these are the questions. Am I environmentally friendly? Yes, no. So this is different from a plotting exercise. This is a percentage exercise. And some of them in grade 5 are great at percentage and some of them aren't. So because they didn't write the questions, what we said to them was, you have to decide the criteria for those 5 questions in order for your class to be environmentally friendly, okay? Or your class. And so, for instance, student A said, my rule is 50% environmentally friendly-ish, 3/5 of them have to be because I think all the questions are of equal value. But then another student, so this for the teacher is a nightmare because every student has its own criteria. My criteria is In Australia, water tanks are really important because we have a lot of water shortage. And then the one about showers is having shorter showers, turning off the tap when you're brushing your teeth, turning off plugs, and then recycling. And recycling is big. So this student wants 100% to recycle. Wouldn't be too so then this is one class data. I don't know if you can see it. We don't have a lot of photos of this. And you can see that it's an exercise in working out percentages as well, depending on the class size. You can see the teachers started working that out. Now in that class, it looks pretty good because 100% of them are recycling and 100% of them turn the tap off. Okay, but the examples of those two students I gave you, which I want to go through, actually, this is the data from their class. So they had much smaller percentages of people doing everything. So then analyzing the data and drawing a conclusion. And what I'm going to do is I'm going to just show you what student A and student B did. Okay, so student A said, our class, which is the one you saw, which you'd have to look back at the PowerPoint again, is environmentally friendly because actually I think 4 of the 5 criteria were more than 50% that they'd done it in their class. So he's happy. But of course, student B is not, because only one question reached their really high level criteria. So across the class, just imagine, you've got 20 students and these arguments. It's just fun. Okay, but that's our class. And so now we want to pose it for all students in Australia. And so we talk about their class first. And of course, they're in Brisbane and they have certain conditions and they know that out in the outback it's different, or down in Victoria it's different. So we have this sample from from the Australian Bureau of Statistics. So they now, and I don't know if you're familiar with this, but I should be able to use this, shouldn't I? Here's the population values. You're drawing 5 because we've got 5 different variables, and the class size was 27. So these are just the first 3 values that the students got. And we set this up for them, and they did the random sampling themselves. And so here is the results for student A. And student A, you can see the percentages, and they learned how to just draw a little plot to get. So you can see that they're, oh, that's really stupid, wrong one. That the percentages are at the top, and yes and no are in alphabetical order there. And so then his conclusion is they're not, since they, sorry, am I on B? B. Oh, student A, okay. So they are, for student A, they were environmentally friendly. But then we ask him, that's for the sample, what about the population? And they're getting the idea that the sample is too small to conclude for that 1,300. That's really good. And so same here, the student B is making a decision and they're not environmentally, since they didn't all satisfy our criteria. And then it's not very certain because it's a small sample and not a representation for all students. Now, isn't that a nice word to be using in grade 5? Well, what we did, and got a bit carried away, and I won't talk about this, I might talk about this a bit more later in the other session. We had them collect 9 different samples and then put together what it was, what it should be. And we wrote this up for the Journal of Statistics Education, which again, it was nice that they liked that paper. And intuitively, for students who go on to university, they can say, look, I did that sort of thing, and so, I sort of got this appreciation about what, we can do with random samples. Okay, now we're moving on to the grade 10 class, and the teachers wanted to do something different. And so we devised an 8-lesson unit. And I'm going to go through them as fast as I can, so I'm not going to stop now. But they had never seen TinkerPlots, and they hadn't done very much anything interesting at all, I have to tell you, tossing coins and that sort of stuff. I mean, coins are nice, but... So we wanted to do everything with TinkerPlots and lead them down to resampling. Okay, so lesson 1, what we again did a few years ago now was we collected data from Australia. And if you know TinkerPlots, there's a book called Digging into a Data with TinkerPlots, but of course it's all US data, and we're saying, come on, we've got to have Australian data. So we wrote a whole book on Australian data. And here are a couple of data sets that we've used. One of my colleagues collected a lot on Australian snakes. And then, well, maybe, I don't know if this is a coincidence, I put this together. Then we have Australian Prime Ministers. Should we be talking about... That just came to me now, because within the next 24 hours, Morrison, who is the current Prime Minister, may not be Prime Minister because we're having a general election tomorrow. But every time I have to fill in a new data value, and it's interesting that, months served might be filled in after tomorrow. We don't know. So, but I just wanted to show you, this is the sort of data sets that we use and that we were exposing these students to. And here's some of the just things that they could do with it. And they'd never done anything, right? So they're just in grade 10 exploring the idea that you can talk about snakes and Australian snakes and whether they are freeborn or have eggs. And this could be related to a big STEM activity, but in this case it wasn't. But here's one for you sports fans, and they loved this one. They had to set it up. So here's the answer. They were given the height and weight and a mystery team they were on. And so they had to then work out a plot and look at the scatter plot, and they hadn't done much with scatter plots before. And so one of those is a rugby league team, and the other one's Australian rules. Now, you probably know a bit about rugby league, but maybe not a lot about Australian rules. For me, Australian rules is a huge game played on a big field that you can dribble, and it's sort of like basketball on... So, anyway, what do you which colour do you think is the rugby? Blue, yes, definitely. They're the guys with, whereas the Australian rules player have to run around a lot, and they're taller and long legs and things. But the students love this. This was one of their favorite activities. Okay, that was lesson 1, just getting them into the data sets. Lesson 2, we were doing dice, the sort of things that, you would be really fairly common with. And but we're trying to indicate some of this randomness, that the variation that you see when you do a small sample size. But of course, with TinkerPlots, within a few seconds, you can do 3,000, and you can. And these students, at least in grade 10, were familiar with percentage and all that, and you could talk about the difference. And then we added that by tossing 2 dice. And you would be amazed that some of the students in grade 10 didn't even have an intuition that it wasn't going to be a uniform distribution. It was kind of worrying to me. So they did it, and you can see up there, if you're into TinkerPlots, how you do it, that little instruction up the top, and I haven't got time to do that. But the kids, again, of course they liked that. And that's what was that one? I don't know what that one was, but now we've done 3,600. So then we moved on to lesson 3, and I wanted to do the hospital problem. So we did it with coins. And this was really interesting because, again, intuitively they had the same views that lots of people have, that it doesn't matter whether you toss a coin 10 times or 30 times, that one might be more likely than the other, and they always say, yeah, it's going to be the same, that won't make any difference. So we have them set this up, and they're learning a lot about TinkerPlots here, which you're just having a show and tell. You can see what TinkerPlots will do. It'll separate the values, and it will put them all, and then you can count the number of heads. And so this is Ted's first draw, and there has to be a bit of explanation, of course, that he's doing it 10 times, but we're saying what would happen if he did this 100 times. How many times would he have more than 60% heads? And so that means 7, 8, 9, or 10, and in the 100 draws he had these are from one of the students, had 27. And Jed is the other one who did it, who was doing it, tossing 30 times. I don't know if I got that right before, right? He had, in fact, 10. Now, those are values that can change a lot. So what are they if you're thinking we'll do it a lot of times? So here are just 2 more trials to show what the students were doing and arguing in class. There's Ted had 15 only that time, but luckily, at the same time, Jed only had 4. And so you're talking about all the implications of this. But I'm just showing the activity that teachers then drew out of this about the fact about the number of tosses that you would do. And then one of my very, very favorite problems, you'd all know, do you all know Cliff Connold's one son problem? This is amazing. 1994, this came out in the mathematics teacher, and he was using ProbSim then, and if you're old enough to know ProbSim, it was the beautiful program before TinkerPlots. Okay, so, and do you all know this Chinese story? They had a one-son policy, and it became unpopular, and it resulted in an imbalance of gender. There were fewer girls, lots of abortions, and question is, what would happen if couples were allowed to have children until they had one son? What would this do? Would the population explode? I mean, that was what people, oh my golly, there'd be so many kids. China would have the worst problem. And would there be an imbalance? Would there be too many girls then? Not now. Well, we know that politically, in the last few years, China has changed its policy. It has dropped the one-child policy, one child. It's a one-child policy. It's the one-son problem. So Cliff, the hypotheses that we set up with the students, and this takes a while, is what's the average number of children going to be if you do have a policy where you can have children until you have your first son, then you stop. And what would the ratio births of girls to boys, boys to girls be? And so you have to make the assumptions, and you talk to the students about what assumptions do you make if you're putting this in the program. And of course that it's a random phenomenon, only single births are considered. We don't talk about twins. In the sampler, it simulates it based on a binomial model with p equal to a half. And then we talk about the fact, we actually say this is a pseudo-random sampler, but it'll do for what we're going to do. And if you're interested in TinkerPlots, setting this up, and we had the students doing this, you can put a boy and a girl in the mixer, and you draw one, and you attribute it to child, call it child, whatever, sex, whatever. But then if you notice on the left, you repeat this until you get a B. And then once you've got a B, you stop. And under the conditions, then you drag down a plot to see those two, and they just float. So in this particular, my first run, I got a girl, then a boy. So that was convenient for me when I was doing this. Okay, then you click on the history button. And the history button is down below the menu there, you can see. And the gray box appears, and then you double click on it, and you create a history. And the history then says, I can collect as many of these as you like, and I collect 199 more, and we get 200 sizes of families, right? And again, in TinkerPlots, you can see that's just floating around. And so then we drag it out. And what I like to do is I like bins, because in bins, for this kind of data, you can see how many children had one boy, how many had a boy and a girl, how many had two girls and a boy, and the largest family, two of the families had 7 girls and a boy. And so you can talk a lot about this. And then if you want to know the average, the mean, which we do means in grade 10, then there's the average for that first simulation. And then the second one is another one to do it. And a lot of talk about, wait a minute, how is this? How does this work out 200? And how are the boys? And, how it's all there. There are going to be 200 boys there, and there are going to be 200 girls there, and how, it's all really a lot of good stuff. Okay, now we want to get into sampling. All that is from the sampler as a random generator with replacement and all this. So we want to do with a finite population. And this one I'm going to do really, really quickly, because we're in Australia, and again, we have data for the 780 convicts, I don't know if you are history, who came out on the first fleet from England to Australia. And we have all kinds of data on them. And our purpose was to say we can have I saw the word purposeful there, is to have a purposeful sample. And one of the ships was the Friendship, and it had 86 convicts on it. And one of the variables was the value in shillings of the crime that they committed. And you will notice, if you look at that, when you think of history, some of those people were coming to Australia for a crime of virtually no monetary value at all. But there were a couple of biggies. And then there are a few on the side. They were coming to Australia for something that had no value, but maybe they killed somebody. We don't know. We're not quite sure. But you see missing data over there in TinkerPlots, which is good for the students to see. So then our question is this typical of the whole fleet? And so then they have to do random sampling of the whole fleet. They get 50 samples of size 86 was the size of theirs, and then plot all that. So we're talking about means now, and the mean of the set of means from the 50 random samples. So we're getting them into something here. And we notice that the mean is 72 point whatever for the whole of the fleet, whereas it's almost the same. So we can say this is a typical ship. And that's not so exciting to you, but we were getting the students into that and a little bit of Australian history. Now we're really into looking at resampling, which is what we're building toward, but they need some skills. And so we're looking at the difference in medians, and this is the activity I hope you might be familiar with, that Mike and Beth, where's Beth, did the, I don't know where Beth is. Hi Beth. The activity that you guys did, memorizing nonsense and meaningful words. And so you don't have to read this, but I'm telling you, the students actually planned the experiment. So we're talking about how do you do an experiment, how do you do it properly, how are you going to time it, you're going to have so many seconds, you're going to have timers, some people are going to do the meaningful first and some are going to do the non-meaningful first, and they as part of the activity, they did a lot of work on this. But so then they had to plot what they got, and I'm leaving out a whole lot here, but they got to the point where this is there were two classes. This is one of the grade 10 classes. So how unusual is this? Okay? So one type of analysis that I wanted them to know, because the box plot was in the curriculum, but they hadn't done it, of course. If we look at Chris Wilde sort of looking at box plots, 3/4 of the nonsense ones were less than 3/4 of the meaningful ones, so we're pretty sure that that's a reasonable difference. And we talked about that. But then, if there's no difference, what happens if we randomly reallocate the data? And you know all this, but we had to talk about it fairly thoroughly with the class. And believe it or not, we had boxes on the class with meaningful and non-meaningful and the data, and we had students drawing each one. So we're saying, you draw, it's meaningful, it was 7. So they actually did it by hand first, which sometimes when you're doing this, you'll do it with dice first or something. But so we actually did it, and that was after the first go. I didn't want to do a second go, so he said, we'll do it in TinkerPlots instead. And so of course that was something very popular with them. And how do we get a result of this? By chance. So that's what they did. And in the sampler, you can see, if you're not familiar with it, that the word type is on a rotating spinner. Is that? No. What is it? The counter. Sorry, the counter over on the end. That counts. And then as it rolls around, one of the random words is chosen, and then it pops out on the other end, and you get the plot. And so in that particular case, the difference was 7 and 8. And then again, there's a ruler in TinkerPlots that can measure the difference. And then the history button, again, keeps track of those differences. And then you can plot 100 trials, and you can see the difference in this particular case. What have we got? One was, is it -5? Yeah, 1 -5, 1 -4, 1 4. So what are we talking about? The difference and which directions they are. Now I'm going to show you a student report, and these are real. These are not edited very much, and I'll let you have a quick look at the report. It's real, all right? So we collected 402 random samples. Less than 0% were the same. We didn't quite like that. But look, this is real, and they're getting the idea. We're 90% sure that this didn't occur by chance. Very much confirms our suspicion that meaningful words are easier to remember than nonsense words. And so but they sort of thought that to start with. And so one of the things that I want to make sure of is that we do some things where we don't expect to be confirming what we think. But that comes at the very end. So the next one then is Alan's. story. And this, I don't know where you found this from, but you've been talking about it for quite a long time. Data are presented in a two-way table, and it's investigating, so this is real world, I'm assuming, that whether people's depression improves if they swim with dolphins or if they just swim in the Caribbean. And I just love this because I'd love to do that. So there were 30 patients randomly selected, and there were 2 treatments. Control, swimming. Are you all familiar with this one? Swimming 4 hours a day for 4 weeks, and then the others were swimming 4 hours for 4 weeks in the presence of dolphins. And so that's the two-way table on no improvement and improvement, and whether they had the treatment control. So you're familiar with all that. So the question is this surprising or not? Is this really helping? Can we do some evidence for this? So the data were put into the sampler, and one of the interesting things is in the sampler, if you're doing chance dice, you got to have replacement every time. But of course, if you're doing a sampling like the previous one and this one, you can't have replacement because you want to use them all up. And so, yeah. Again, the treatment goes around dolphin or control, and then the data are allocated, and that's one of the outcomes. And of course, you get 4 categories, but you can use the history button to be associated with any of those 4, but we chose the dolphin improvement because that's sort of the fun bit. And then again, you click on that, you follow the history button, and then you can collect the data. That is the original data down there, and that's one of the reallocations that you can see there. So again, we did 199 more random samples, and this is what we came up with. The following results, that there were 5 that were more than, what have I got there? Can't remember now what that was. Oh, it was 10, sorry. It was 10 that had improved. I'm getting confused. There were 10 that had improved, hadn't they? That 7 that had come up in my sample, I was getting confused about. Right, there were 5 times out of 200 that a result as strong as 10 people improving would occur by chance. And then they each did this. So they got different values, and again, they have to write up what they're doing about that. So the final lesson was an assessment, and I'm not going to talk about it except that we gave this to them, and I gave them these 2 samples. These are again from the Australian Bureau of Statistics Census at School site, and it's comparing the reaction time of boys from year 10 and boys from year 5, and boys and girls in year 10. And if we look at those, I think we would agree that although it looks like that the boys are a little bit faster than the girls, in fact, they're not really statistically significantly different. We don't use that word. But for the boys in year 5 and 10, there was a difference. So this is what we gave them in an assessment and said, can you tell us which? And so they would have done some activities on that. So that is a quick run through the range of activities that we're doing in Australia in our projects. They are not happening in every school. We would love them to be happening in every school, but of course they're not. And I've been asked by the NCTM to tell you about some of the books that they have produced, and they've said, if you have a chapter and any of the books that we produce, can you advertise it when you talk to other people? So this is the book that's down in the right-hand corner, and they have said that they will give a 20% discount on anybody at this conference who wants to buy this book, and I've got some bits of paper if you want to see, if you actually want to know what's happening in grades 5 to 7, which is what that series is. I love the NCTM. And thank you. I would love you to come to Tasmania. We are one of the most beautiful places in the world, and I live just off the water from that upper right-hand corner beneath Mount Wellington. It's lovely. Thank you.
We have time for a question or two for Jane. Any questions?
It's all too fast.
Question? John.
So this was really interesting. I really enjoyed the discussion of fundamental concepts and ideas. I'm wondering, in the curriculum, is there a place for the concept of models? Mathematical models, or just even without the math, this notion of models and trying to infer what sort of model might have created these data?
Not much, no. Probability and statistics is a subset of mathematics, and if I look through the number of topics, it gets 23%. And even within the rest of mathematics, it's a fairly conventional algebra and number, geometry, looking at the curriculum. And when you would get to the senior levels, there's a little bit more of that, but often it is very closely related to physics rather than what I would call, and what I think people generally talk about as modeling. And I have a little difficulty myself in using that terminology. One of the books that's in this series is a really good one. Some of you would know. That one up the left corner has work on thinking about the transition from a mathematical model to a statistical one where you add variation to the mathematics that's in the model. And we haven't been sophisticated as that at school because we don't have the mathematical models to work with that the students have. So I wouldn't say that it's strong, no.
Another question? We have time for a quick one. Rob.
So in third grade they work without TinkerPlots, in fourth grade they work with TinkerPlots, fifth grade they do something more sophisticated. You must have students in fifth grade who didn't have the third grade experience.
Where they help.
Do you have data about how different, how well?
It's not a strong sort of experimental thing, but yeah. The students come in, and in fact, believe it or not, I mean, TinkerPlots is so easy that if we put somebody who hasn't used it next to someone who has, and of course, this is the world of the real world. In the beginning, we had the school's laptops. Next year, the students have to have their own laptops, which is almost worse because, as you know, TinkerPlots is not free. So I bought 70 licenses for the school, and then the kids have to use some of those licenses, and then they get a new computer because their parents buy them a new computer. And so we end up with a lot of them actually working together, which we can't worry about. But that helps because the ones who come in grade 5 have people showing them. And some of our kids are very, very good at it, and they will help lots of other kids in the class. And there are not many that don't like TinkerPlots. In fact, in the first project, the one we did in Brisbane, every time we arrived in the school, the kids said, "Oh, they're the TinkerPlots ladies, they come." And in that school, we actually started in grade 4, so we started them straight off with TinkerPlots in that school. Yeah.
Great. Well, thank you very much.